Welcome to our last section of our unit on electric current, resistance, and Ohm's law. In this section, we're going to talk about AC circuits. Thus far, everything we've done has been a DC circuit, a direct current circuit. If you think about the simulations we've watched, the electrons came out of the battery and moved around the circuit, always going the same direction. Direct current. AC circuits work differently. And I wanted to spend a little bit of time here because while a great deal of what we do every day does involve DC, almost all of it also involves converting AC to DC. So let me give you an example. I have my laptop. I take and I plug my laptop into a standard household outlet. That standard household outlet produces 110 volts AC electricity. Okay, but I just said my laptop uses DC. So if you look at the power cord on your laptop, there is a large box, a large chunk, probably something you very much wish wasn't there. That box is an AC to DC converter and changes what comes out of the wall into something that the electronics in my laptop actually need. The same thing with the blocks that are at the end of the chargers for your smartphones. Many electronics have a converter. You may not be able to see it. For example, the one for a television would be inside the television and not on the power cord. Things that don't have converters are blenders and stoves and dryers, things like that. So why is the world powered by AC? This is a bit of a history lesson. I pulled up a website which goes into that a little bit, but it really all comes down to the 1893 Chicago World's Fair. Which here is my website. I'll pull it up for you. The 1893 Chicago's World's Fair. This World's Fair was big. And they wanted it to be powered with the new electric lighting. So they asked for bids. And two groups came out. One was Westinghouse, and the other was what is now GE, but was formerly Edison Lighting Company. Westinghouse, the brains behind it, if you will, was a physicist by the name of Tesla. GE was Thomas Edison. And very different proposals. Edison's was for DC lighting. Edison's light bulb, his incandescent light bulb that he invented, was for DC lighting. Westinghouse and Tesla proposed AC, and they won the bid. They won. And I mentioned Chicago World's Fair was huge. It was huge, and everybody wanted to be like the Chicago World's Fair. And since it was AC, everybody else wanted to be AC. In the end, I think this was good. Regardless of the World's Fair, it's good that the world is AC. It's easier to produce AC electricity. It comes about naturally when you rotate something. So when a wind turbine rotates, or a steam-powered turbine, or whatever turbine you want, that produces naturally an AC electric current. It's easier to transmit AC. It is also easier to shift from AC to DC than from DC to AC. It is also easier to convert within different voltages and currents in AC than it is within DC. So lots of good reasons for it to have happened. If you want a good read about the Chicago World's Fair in 1893, including the war between Tesla and Edison to win this bid. So let's go and look at some AC circuits. I'm going to pull up a circuit construction kit. This is similar to the one that you have seen and worked with a little bit in lab. This one, however, is an older version that runs in Java with the functionality that you can look at AC instead of just DC. So this is the one I'm using. So I'm going to, instead of pulling out a battery, I'm pulling out the AC current source. And I'm just going to pull out a light bulb again. And as we've done in the past, connect the wires. And now look. The electrons move, but they go back and forth and back and forth and back and forth. They alternate direction. Therefore, AC is alternating current. Okay. And as you can see here, the light turns on and turns off, and it turns on and it turns off as the currents slow, stop, and then change direction. Every time the current stops, the light turns off. We can change the frequency. Right now it's at half a hertz. If I speed it up, it's at 1. You can see there comes a point here, I'm only at 2 hertz, where yeah, we can see something's going on, but it's not nearly as clear as it was at half a hertz. I slow it way down here. And that is the key to this. In the US, our AC electricity operates at 60 hertz, and standard wall outlet is at 110 volts. It is different in Europe. Europe is at 50 hertz and I believe closer to 200 or 220 volts, which is why if you go to Europe, you have to have a converter. You can't just take your curling iron or your hairdryer over to Europe and plug it in. You have to have the correct converter so that you can power things properly. Okay. The electrons change direction. Isn't that fun? So now let's think about, why don't our lights appear to flicker? Well, remember the frequency bit. At half a hertz, we could see the fluctuation, but as soon as we got up to 2, it was much harder. Our lights are at 60 hertz. They are flashing, but they're flashing so quickly that our eyes and our brains can't perceive it. I have heard told of people who can perceive this. To my understanding, it makes for a very difficult life. Okay. This concludes our brief overview of AC circuitry. In the next unit, we're going to move into slightly more complex circuits and look at how to analyze them.